Now we have learned that the potential energy curve can be used to characterize the material's elastic properties. Now we will use the curve to compare some different types of materials. We also know that the potential energy curve can be derived from the atomic bondings. So we know that materials with different bondings between the atoms will have different shapes of the curve. And that's actually what is shown in the first schematic picture here. If you look at plastics or polymers, they are bonded by van der Waals forces between the carbon chains, and these forces are very weak. It means that we tend to get, for polymers, we tend to get a curve that has a rather flat curve around their equilibrium point. If we go to metals with metal bonding, which are stronger, we will have a deeper curve with a more deep minimum point. And if you go to ceramics, generally they are bonded by ionic bonding, which are very strong, and here we have the deepest minimum in this curve. Now we can also compare these. We know that the shape of the curve, and as we said, the second derivative in the equilibrium point directly gives us the elastic modulus, or the stiffness of the material. So it means that if you look in a stress-strain diagram for the different types of material, you will get the highest slope, the largest stiffness, or the highest elastic modulus for the ceramic materials, which has the deepest minimum in the potential energy diagram. Then it comes to metal with somewhat smaller slope, and polymers will have a very small slope, which have the weakest bonds. There are also other properties than the elastic properties that can be coupled to the energy potential curve, and thus also be coupled to the atomic bonding strength. The properties I'm talking about now is thermal expansion and melting point. So we start looking into that also. Here again is the potential energy curve, as we see it here, which consists of the sum of the repulsion forces and the attraction forces. We have looked at this minimum point and said that this is actually atomic distance. But if you look close into this is only valid at 0 Kelvin temperature. That is at absolute zero temperature, when the atoms are absolutely still. If you start raising the temperature, the atoms will vibrate between the two arms of the curve. And if you raise the temperature to a level that we have this potential energy level, the vibration will be between these two blue points. And now we see here that the curve is not symmetric. And it means that when it vibrates between these two curves, we have a shift from the original position. We'll have a shift from this position to that position. And that is actually the thermal expansion of the material. So now we realize that the thermal expansion will be dependent on how much this asymmetry really is as a function of the raised temperature. If I have a very wide curve as a result of weak bondings, we will have large thermal expansion. If I have a very deep minimum here, which is a result, if I have a very strong bondings, we will have a small thermal expansion. We can also see another feature in this figure. If you continue to raise the temperature from this level, we will follow the curves, and then we will come to the inflection point of this curve. And here, this corresponds more or less to the melting point. It means that when we raise the temperature above this point, the atoms will float away and don't connect to the other ones again. Somewhere here we can see the melting point. And that means that the shape of the curve also determines the melting point of the material. We will now use this knowledge to compare two different materials. Here we have the potential energy curve for two materials. It's for lead, with a rather wide curve, with a rather shallow minimum, and we have another curve for tungsten, which has a deep minimum and a rather sharp edge here. If we start discussing the thermal expansion coefficient and look at tungsten, we will see that when we increase the temperature from 0 and upwards a bit here, the vibration between the two parts of the curve will not implement a large difference between the starting position and the average position. It means that we can increase the temperature rather high for the tungsten and still have more or less the same atomic distance. It means that we have a very small thermal expansion coefficient when the curve looks like this. Instead, for lead, which has a much wider curve, we see that when we increase the temperature from the 0 temperature and upwards, we will have a clear difference between the starting position and the average position between the vibration points. If we also discuss the melting temperature, as we said, the melting temperature comes here at the inflection point of the curve. And a curve like this with a rather shallow and wide curve with a shallow minimum will have an earlier inflection point. The melting point will be closer to the absolute 0. While in the case of tungsten, now we can't see the curve, how it continues here, but here we will have a much larger difference and a much higher melting point. And it's of course logic, because the differences here and the curve's shape are a result of the bonding forces between the atoms. So if we have very strong bonding forces, we will have a deep minimum, and we will have all these three effects of the three properties. That means that we will have a high elastico-Young's modulus, which will be obtained through the second derivative at this point. We will have a low thermal expansion coefficient, and will be a high melting point. If we go to a curve like this, we'll have the opposite. The second derivative in this point will give a smaller elastico-Young's modulus. This effect gives a larger thermal expansion as the curve is wider, and the melting point will come earlier. We have a lower melting point. These three properties, that all can be coupled to the shape of these curves, and the shape of the curves are directly a function of the binding forces. All these properties are called structure-independent properties, as they are only dependent on the bonding strengths between the atoms and not depending on the structure of the material. We will end the discussion about the structural properties of materials by looking into the periodic table of the elements. As the position of the elements in that table is coupled to that atomic bonding strengths and atomic bonding type, so it will be interesting to see how we can see some of these properties, how they are changing when we move around in the periodic table of the elements. Here we see a diagram with the melting points for a number of elements organized based on the different periods in the periodic table of the elements. We can see here that for elements in period 4, starting with potassium, which is group 1, calcium group 2, and so on, we see that group 2, 3, 4, 5. Here we have vanadium, and chromium in group 6 has the highest melting points in this period. If you look at period 5, we see the same pattern. Group 1, 2, 3, 4, 5. So we see group 5, 6, 7, 8 are at the top here. And the same thing is for period 6. The groups 5, 6, 7, 8 have the highest melting points. Now we know that the elements that have the highest melting points also have the highest stiffnesses, that is, the highest Young's modulus. And also these elements have the lowest thermal expansion coefficients. So only by looking into the periodic table of the elements, we can make a lot of judgments about these structurally independent properties. We now know by looking into the diagram where we can find the stiffest materials or the materials with the highest melting points. We also know why we have these properties, because they are coupled to the bonding strengths between the atoms.